Hi Calculus, we are going to go through these homework assignments. Okay, 1. Does the limit exist at x is equal to 2? Put in your imaginary vertical line and trace the graph. This is coming in here on the left, but on the right it's coming up here. That is a bad date. So that is not, there is no limit. No. Is the graph continuous? No, because step 2 fails. We have a y value, we have step 1, but we don't have step 2. So we would say the limit dne, step number 2 in your definition of continuous. Okay, problem number 2. Does the limit exist at x is equal to 3? If we put in our vertical line and we trace the graph, from the left we're coming in, and from the right we're coming in. That's a great date. So the limit does exist. Yes. Is the graph continuous at 3? Well, let's go through our steps. Is there a y value at 3? No, there is no point. So we would say the graph is not continuous, and we would also say there is no y value at 3. All right, there's no point, and that is step number 1. Okay? You could also say that f of 3 dne. A lot of ways you can say it. All right, let's keep going. Number 3, does the limit exist at 4, negative 4? Well, here is a vertical line through negative 4. If you trace the graph, the left and rights are meeting at the same place. So the limit does exist. Is the graph continuous? Well, there is a y value right there. There's no hole there, so there's a y value, and there is a limit, and they are in the same place. So we would say it is continuous. All right, number 4. Now we're looking at negative 5. If we put our vertical line through negative 4, or negative 5, excuse me, does the limit exist? Yes, the left and the rights are meeting in the same place. The limit exists. Is the graph continuous? Yes, it is. I can draw it without picking up my pencil, and when I use the definition, there is a y value here. There's no hole here, so there is a y value, and there is a limit, and they're in the same place. Number 5, is the graph continuous at 2? If we put in our vertical line, as we trace the graph on the left, it's going to infinity, up and up and up and up. As I trace the graph coming from the right, the graph is going down, 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 negative infinity. So that left and rights are complete opposites. There is no limit. Is the graph continuous? No, because there's no y value here. Along a vertical asymptote, there's no point. So we would say no, and we would say f of 2 dne. All right, there's no y value. Oops, forgot the v. Okay. Number 6, is the graph continuous at 5? Don't be fooled. We're not looking over here. We're looking here. So if I trace the graph here, from the left and from the right, we're meeting in the same place. Yes, there is a limit. Is the graph continuous? Yes, there's a y value here. Again, there's no hole, so there is a y value. There is a limit. Great date. The left and rights meet, and they're at the same value. So that is yes and yes. Number 7, does the limit exist at x is equal to 1? Well, if we put in our vertical line, if we trace the graph, the left and the rights meet in the same place. There can be a limit at a hole. Think about it. That's just a pothole. You can hold hands on your date over the pothole. There can be a limit at a hole. So there is a limit. Yes. Is the graph continuous at 1? Well, let's go through the steps. There is a y value. There's a point right here. There is a limit. So there is step 2, but they are not the same. The y value is up here. The limit is here. So we would say it is not continuous, and we would say that the y value, f of 1, does not equal the limit. Does not equal the limit as x approaches 1 of our function. So that is step number 3 that fails. Problem 8. Does the limit exist at x is equal to c right here? Well, if we put in our vertical line, we can see right off the bat that there is a step here, and the left and the rights are different. So there is no limit. Is the graph continuous? Well, we have step 1, there is a y value, but we don't have step 2. So we would say the graph is not continuous. We would say that the limit as x approaches c of our function d n e, and that is step number 2. Problem number 9. Does the limit exist at c? Well, if I put in my vertical line and trace the graph, the left and the rights are meeting. There can be a limit at a hole, so the limit does exist. Is the graph continuous? Let's go through our steps. Is there a y value here? There is no y value here because there's a hole there. So we would say no, and we would say step number 1 fails. F of c, d, and e. There is no y value. Finally, number 10. Does the limit exist at x approaches c? Well, if we put in our vertical line and we trace the graph, the left is here, the right is up here. There's a step in the graph, so the limit does not exist. All right, is the graph continuous at c? Well, if we go through our steps, there is no y value right here. Those are both holes. So we would say it is not continuous, and we would say f of c, d, and e. No y value. All right? And that is step number 1. Okay, number 11. We just need a graph that is continuous at 3, and there's a cusp there. So we go out to 3, 1, 2, 3, and we put in a sharp point. And you can put any graph you want there, but it needs to be a sharp point. Okay? That's all you need, a sharp point at 3, without a hole, continuous. Number 12. There can be no value for f of 5, so it means at 5, 1, 2, 3, 4, 5, we need a hole. It can be anywhere. Okay, so there's no y value, but there has to be a limit. Has a limit as x approaches 5. So the left and the rights have to be coming in at 5. Okay, so we've got it. No y value, but there is a limit at 5. Okay, 13. There is a vertical asymptote at 6. Okay, vertical asymptote. We like to put in a dotted line. We like to label it with the equation, so the graph has to be coming closer and closer to that without ever touching it. So there's a lot of different ways you can do it. I'm just going to put one side going up, and I'll put the other side going down. So you just need a vertical asymptote at 6. That's a line that a graph never hits. Okay, 14. There's a step discontinuity at -2. That means that there has to be the left and the rights coming in at different places. All right, and the other thing that we have is we need this point, okay, right here. F of -2 is equal to 10. That gives us the point -2, 10. So I'm going to put that point on the graph. I'm just going to scale this by 10s, or by 2s, excuse me. 2, 4, 6, 8, 10. So I need a point right there. There's my point. All right, and I need a step there. So I'm going to put the graph out here to the left, and then I'm going to go down a little ways. Doesn't matter how far, and I'm going to put in a hole, and I'm going to have the other side going this way. So there's a step discontinuity at -2, so I've got my step. My left and rights are different, and I have this point on the graph right there. Okay? Okay, for 15, the limit as x approaches 1 is up at 4. So as x approaches 1, the y value has to be up here at 4. So your date has to be coming in at 4. But then it also says this point is on the graph. So this right here, this tells us that the point 1, 6 is on the graph. So I'm going to plot that point. That's where my point has to be. But my limit, my date has to be up here at 4. So I'm going to need a hole here because I can't have two y values. So I need a hole here at x is equal to 1, and there's my limit. I'm just going to go like this. Okay? So again, there's a lot of different ways you can draw it in, but the limit has to be, the date has to be coming in at 4, but your point is up here at 1. Okay, for problems 16 through 18, you have to sketch the graph. So when I put this function into y equals and I graph it, I come up with this. Okay, now there's obviously a discontinuity at -3 here. We know, because if I plug in -3 for x, I'm dividing by 0. I know there has to be a discontinuity at -3. I can't see it in my graph because my calculator doesn't know how to pick up the pencil and put it down. But I can see it over here in my table. There is definitely an error here. So the discontinuity here, as it is at x is equal to -3. All right, so the discontinuity is at x is equal to -3. And what step fails? Well, there is no y value. There's no point here. All right, so step number 1 fails. All right, f of -3 does not exist because there is a vertical asymptote here at -3. This is a vertical asymptote right here. Okay, number 17 is very similar to number 16. We definitely have a discontinuity at 11 because if I plug in 11, I'm dividing by 0. Here is a picture of the graph. I just changed my window out to 20 so I could see it, but this is definitely a vertical asymptote here at x is equal to 11. So we can see it on the graph. We can also see it in the table right here. All right, there is our discontinuity. So my discontinuity is at x is equal to 11, and we can say that step number 1 fails again. All right, there's no y value at 11. F of 11 does not exist. Okay, number 18 is the graph of the cosine, and if you remember from pre-calc, hey, the cosine is continuous everywhere. There are never any discontinuities. So we just say this guy is continuous everywhere for all values of x. Okay, number 19, if you look at this graph of 3 plus the square root of x minus 2, here is the picture. So where is it discontinuous? Well, there's no graph to the left of 2, so it's definitely not continuous at 2. But what step fails? There's definitely a y value at 2. If you look in your table, there's no hole. It doesn't say error, so we do have a y value, but we don't have a limit. If I put in my imaginary line through 2 right here, there is definitely no left limit over here. So step 2 fails. Alrighty, step 2 fails. The limit as x approaches 2 of this function does not exist. There's no left limit at all. Okay, finally, number 20, we have a trig function, a sine of x minus 2 over x minus 2. Here's the picture of the graph. It's a sinusoidal curve. We know when we plug in 2 for x, we're going to be dividing by 0. So we know there has to be a discontinuity at x is equal to 2. You cannot see it on the graph because the calculator does not know how to pick up its pencil and put it down. So you have to check right here. There is an error. There is a hole at 2. All right, so our discontinuity is at x is equal to 2. And that's the first step in the definition. Step 1 fails. All right, f of 2 does not exist. There is no y value at x is equal to 2. Okay, I hope this helped. Please let me know if you have any other questions. Thanks, Calculus.